Alrighty, guys, welcome back to MAC1140. Today is another fun day for us where we get to play around with matrices. I am going to show you first and foremost how to multiply two matrices, which is a big deal. And then I'm going to do my best to kind of convince you that matrices are functions in a slightly weird way that's going to require you to think somewhat open-mindedly about what a function is. Your exams are graded. If you took a makeup exam, they're not graded yet, but if you took the exam with the rest of the class, those grades are in. I want to just encourage you to look at all the comments, check both the written work, because I've annotated your written work where there are mistakes, I've made corrections, but also make sure to check the test itself in Canvas, because I've typed several comments in there where a written work comment wasn't applicable or appropriate. So please look at both of those things. Yeah, question?
Yeah, so the video from yesterday, I was trying to look over to see what you said about the test because I didn't hear it very well. And it was the video from Thursday, not Monday.
Ah, interesting. So the video from yesterday, 8/2, that's the wrong link.
Yeah, you uploaded the video from the 29th.
Strange. Let me take a quick peek here. Tell you what, let me not, it says 8/2 here, but we're saying that the actual video is not correct. Yeah, I see. All right. I'll leave this up as a reminder to replace it. I must have uploaded the wrong clip. Sorry about that, guys.
No worries. Could you go over again what the test is going to be like Thursday?
Oh, so your last midterm test is going to be given as a take-home test rather than a proctored in-class test. That way we have a little bit more time to talk about sequences and series, it's nice to introduce that notation to you here so you're not seeing it for the first time in calculus. So that's all. So the way the exam 3 is going to work is on Thursday, I'll upload a PDF, which you guys will download and print. There's going to be a little honor pledge on it that you have to sign. Says, I swear I didn't Google or talk to anybody else. You'll fill it out kind of like a worksheet. You take the test at home. You're allowed to use your notes, just your notes, but you're allowed to use your notes. And then you will scan and submit those the same way you scan and submit written work for any other test. It will be given out on Thursday, and it will be due on the day of the final, which is Monday the 9th.
Awesome. Thank you, Professor.
Yeah, of course, no problem. All right, so this is MAC1140, which is pre-calc. It's a lecture. And today is the 3rd of August, 2021. Today, I'm going to do a few things. We're going to learn how to multiply matrices. So this is more algebra of matrices. We're going to finish section 10.4, and then we're going to talk about matrix inverses, which is 10.5, and something called determinants, which is from 10.6. And the order of the latter two sections, 10.5 and 10.6, are a little controversial. So it is the nature of linear algebra. People love to push determinants to the very end because they're kind of weird. But also they're very useful for talking about matrix inverses. And it turns out matrix inverses, this is really the kind of big tool for solving systems of equations. But the way you know if a matrix is invertible is by calculating its determinant. So I'm going to teach these two together, and that will be the end of our study of matrices. Kind of the idea is that a matrix inverse is the closest thing we have to a concept of dividing matrices. So first we have to learn how to multiply matrices, and then I'll introduce the notion of an inverse. And then we'll talk about determinants, and then I'll come back and show you how to calculate inverse matrices. All right. So first, multiplying matrices. I used to do this a little bit different. I used to just give you the recipe and then practice. But I think I think the right way to do this is to tell you how to multiply certain kinds of matrices first, and then show you how the general case follows from that. So the first thing I'm going to introduce here is something, and you may have heard of it, called the dot product, or multiplying row and column matrices. So I'm going to step away from the way the book does things just a teensy bit here, and then I will come back and show you the way they describe it. But I think this is the right way to do it. Let me just crack your text so I can be consistent with the notation. Okay, so that's where we were. Very good. All right. So by a row matrix, what I mean is a matrix with one row. With only one row. And by a column matrix, you can probably guess, I mean a matrix with only one column. These together do have a special name. These are kind of traditionally called vectors. And if you've taken any physics, you've seen the concept of a vector there, it's the same thing. But mathematicians use a slightly different notation. The way you multiply a row matrix times a column matrix is what in other settings we call a dot product, but I'm just going to show you how to do it. So here's how you multiply, how to do it. If I have, let me use the notation we're using before. If I have a row matrix like A11, A12, A13, and I want to multiply that by a column matrix like B11, B21, B31, the way this is done, this is actually going to produce a number. And that number, so sometimes the dot product is also called scalar product because the result is a scalar or a number. This is going to produce a number, not a matrix. And that number is A11 times B11 plus A12 times B21 plus A13 times B31. So you kind of this times this, plus this times this, plus this times this. Right? That's how it's done. So you take these guys and you multiply them with their buddies over here, one at a time, this times this, this times this, and this times this, and then you add those up. Larger matrices there are some rules. Like in order for me to do this thing I just did, the row matrix has to be as long as the column matrix is tall. You see that? In order for me to have like something to multiply each of these A's by, I had to have the same number of B's. So if this is 3 long, this has to be 3 tall in order for me to form this product. If this was 3 long and this was 2 tall, then I wouldn't have anything to multiply the A13 by, right? He would be left lonely. And it's not like if this is too tall, I can just pretend this is 0. It's different than saying this is 0 or there's nothing at all there. Similarly, to multiply larger matrices, they have to have dimensions that are amenable to a process like this. So first, we can only multiply two matrices if the appropriate condition on their dimensions is met. The way we're going to do this is take rows of the first matrix and multiply them by columns of the second matrix, just like we did here, rows times columns. So the length of the rows has to be the same as the height of the columns. So in other words, if A is Aij is an M by N matrix, I'll think of this as my first matrix, and B as entries Bij is a P by Q matrix, then I need the length of the rows of A to be equal to the height of the columns of B. Well, the length of the rows is the number of columns, right? This guy right here, you can think of this as a 1/3 matrix. It has one row and 3 columns. And this guy right here is a 3/1 matrix. So the length of your rows is the number of columns you have. And the height of your columns is the number of rows you have. So in order to have those match up, where the length of the row is the height of the column, right? These are both 3. You need these inner numbers to match. You need the number of columns of A to be equal to the number of rows of B. So the condition, if A and B are two matrices of arbitrary dimension, these we can form the product A times B if and only if N is equal to P. Remember N, this is the number of columns of A. Which is the same as the length of the rows of A, and P, this is the number of rows of B, which is equal to the length, or height, I should say, right? Height of the columns of B. So the length of the rows in the first has to be equal to the height of the columns in the second, so that we can do this sort of thing. So if you've got an M by N and you want to multiply it by a P by Q, N needs to be equal to P. And another neat fact, the resulting matrix will be M by Q. So like in that example with the row and the column here, we had a 1/3 that we multiplied by a 3/1. We were allowed to do that because the inner dimensions match. The number of columns of the first is equal to the number of rows of the second. And the result was just a number. It was a 1/1 matrix. So the way I think of this is the inner numbers have to match, and the result is the outer numbers. So if you want to multiply an M by N with a P by Q, you need to have N equal to P, otherwise you just can't do it. And the resulting matrix will be an M by Q. Now, how do you do it? The ith, jth entry in the resulting matrix is the dot product of the ith row of the first matrix with the jth column of the second. Let me show you. So for A, I will use a 2 by 2 matrix, 1, 3, -1, 0. And this is a 2 by 2. For B, I will use the 2 by 3 matrix, -1, 5, 2, 0, 4, 7. And this is a 2 by 3 matrix. So are the length of the rows of A equal to the height of the columns of B? Yeah. There's two, the rows here are of length 2. In other words, there's 2 columns. That's the second number. And in B, there's 2 rows, or the columns are of length or height 2. So this has 2 things, this has 2 things. So I can take a row from the first and multiply that row by a column from the second. And A times B here is going to be a 2 by 3 matrix. So it's going to have 2 rows, 3 columns. I'm going to need lots of space for this because I'm going to write everything out. So what goes in the 1, 1 position? Well, I'm going to take the first row with the first column. Maybe I'll write this out. This is going to be a 2 by 3. I take the first row of A times the first column of B. Here in the next position, I would take the first row of A and the second column of B. I didn't give myself enough room. In the third position in the top row, I would take the first row of A and the third column of B. And then in my second row, I would take the second row of A and the and the first column of B. In the 2, 2 position, I would take the second row of A and the second column of B. And in the 2, 3 position, I would take the second row of A and the third column of B. Right? So you do the row times column product in each of those entries. So it's a big calculation, and the result is a 2 by 3. So let's do it. The first row of A is 1, 3, and the first column of B is -1, 0. So in the 1, 1 position, I do 1 times -1 plus 3 times 0. Let me zoom in a little bit. Can't quite see everything. All right, come on, camera. All right. So the first column of A, 1, 3, and the first column of B. So 1 times -1 plus 3 times 0. In the 1, 2 position, I take the first row of A and the second column of B. So that's going to be 1 times 5 plus 3 times 4. And in the 1, 3 position, I take the first row of A and the third column of B. So that's going to be 1 times 2 plus 3 times 7. Everybody see? First row of A, first column of B is this. First row of A, second column of B is this. First row of A, third column of B is this. Now we come down to the second row in my result. I take the second row of A and the first column of B. So that's -1, 0, and -1, 0. So that's going to be -1 times -1 plus 0 times 0. In the 2, 2 position, I take the second row of A and the second column of B. That's -1 times 5 plus 0 times 4. And in the 2, 3 position, I take the second row of A and the third column of B. That's -1 times 2 plus 0 times 7. And what do I get? Well, -1 times -1 plus 3 times 0 is -1. 1 times 5 plus 3 times 4 is 5 plus 12 is 17. 1 times 2 plus 3 times 7 is 2 plus 21 is 23. -1 times -1 plus 0 times 0 is +1. -1 times 5 plus 0 times 4 is -5. And -1 times 2 plus 0 times 7 is -2. So here is the matrix A times B. So you take products of rows from A with columns of B. It's a little weird. It's a little weird. But this is done for a reason. Again, this is done because matrices are really functions. And we want the multiplication of matrices to be the same as the composition of those functions. Remember function composition, plugging one function into another. So if A is a function here and B is a function here, then A times B is what you get by plugging the function B into the function A. And that would be a new function. That would be this matrix, AB. Let's get a little more practice. What if A and B are both square matrices? Maybe A is the 2 by 2 matrix, 5, 7, -3, 0. And B is the 2 by 2 matrix, 1, 2, 9, -1. Since these are 2 by 2s, I can actually multiply in whatever order I want. I'd like to point out, let me come back here. I can multiply A times B here because the number of columns of A is the same as the number of rows of B. But I couldn't multiply B times A. I couldn't do the multiplication in the other direction because the number of columns of B is not the same as the number of rows of A. So the only matrices, the only time you can multiply matrices in either order is if they're both square and of the same dimension, like 2 by 2s and 3 by 3s. If they're both 2 by 2s or both 3 by 3s, then you can multiply A times B or B times A. Let's go ahead and form the product AB here. That's 5, 7, -3, 0 times 1, 2, 9, -1. I like to put the resulting matrix down here. So I go 5 times 1 plus 7 times 9. Oh no, we're going to see how bad my arithmetic is. Then in the 1, 2 position, I take the first row of A, second column of B. So that's 5 times 2 plus 7 times -1. In the 2, 1 position, I take the second row and first column. So that's -3 times 1 plus 0 times 9. And in the 2, 2 position, I take the second row and second column. So -3 times 2 plus 0 times -1. So that's that matrix product. And I can clean it up. So 5 plus, what is 7 times 9? That was 7 times 10 would be 70. Minus 7 is 63. So 5 plus 63 is 68. 5 times 2 plus 7 times -1 is 10 minus 7 is 3. -3 times 1 plus 0 times 9 is -3. -3 times 2 plus 0 times -1 is -6. All right, there's A times B. Now I said we could multiply here A times B or B times A. Let's multiply B times A. So BA would be 1, 2, 9, -1 times 5, 7, -3, 0. The result is again going to be a 2 by 2. Let's crunch it up. 1 times 5 plus 2 times -3. That's my 1, 1 position. My 1, 2 position is going to be 1 times 7 plus 2 times 0. And first row, second column. My 2, 1 position is 9 times 5 plus -1 times -3. And my 2, 2 position is 9 times 7 plus -1 times 0. Let's see what we get here. Well, this is 5 minus 6, which is -1. Uh-oh. This is 7 plus 0. This is 9 times 5, which is 45, plus -1 times -3 is plus 3. So 45 plus 3 is 48. And 9 times 7 is 63 plus 0. So what have we just demonstrated?
That it changes when you change direction.
Yeah, this matrix is definitely not equal to this matrix. This matrix is AB. This matrix is BA. They both came from multiplying the same two matrices, but the result is different. This is some fucky stuff. So observe. Even when you conform the product, it's quite possible that AB is not equal to BA. And this again should remind you of function composition. Plugging F into G does not always give you the same thing as plugging G into F. Function composition is not commutative, and neither is matrix multiplication. But it's weird, right? It's weird because it's the first time you've seen something called multiplication that doesn't obey this rule. No, certainly with numbers, 3 times 5 is the same as 5 times 3. With regular variables that just represent numbers, x times y is always the same as y times x. But with matrices, it's not true. Even if you're lucky and both products exist, it's possible for AB to exist, but BA to not exist, right? If the dimensions don't match up right. Maybe you can form the product in one way, but not in the other. So matrix multiplication we saw last time is associative. Oh no, we didn't, sorry, we didn't see that. So let me, some properties of matrix multiplication. So first, yeah, associativity. A times BC is going to be the same as AB times C. This works. I'm not changing any order here, right? I'm not flipping, putting a B before an A where previously there was an A before a B. I'm just saying that if you multiply B times C first and then multiply that by A on the left, that's the same as multiplying AB and then multiplying that by C on the right. It's called associativity. It's also distributive. A times B plus C, that is the same as AB plus AC. And it's left distributive as well. B plus C times A, again, these are all matrices, is the same as BA plus CA. We have to be very careful about multiplying from the left or from the right because they don't necessarily mean the same thing. And these rules, we really want these rules. Without this being true, the algebraic structure really isn't there. If you go on to study algebraic structures as a thing, people do that, they're called algebraists, you'll discover that most interesting algebraic structures are not necessarily commutative, but they are definitely associative. You gotta have this. Without this, you're in like a monoid, which is a fucky little shitty algebraic structure. Above monoids are groups. Groups are places where you do have associativity. Above that, you have rings, and above that, you have fields. Numbers form a field, right? Rational functions form a field. Matrices definitely do not form a field. They don't, they're a non-commutative ring. Okay, so not necessarily commutative. Why do we care about these things? What's the purpose of introducing matrix multiplication when we've been talking about systems of linear equations? Well, it turns out that there's a very real reason to do this, a very concrete reason to do this. It's not just studying bizarre algebra structures for their own sake, although that can be fun too. Consider the following matrix equation. We looked at some matrix equations last time. Only now I'm allowed to multiply matrices. So here's a matrix equation. 1, -1, 3, 1, 2, -2, 3, -1, 5. It's a matrix. And I'm going to multiply this matrix by the column vector x, y, z. And I'm going to set that whole thing equal to the column vector 4, 10, 14. Notice that the dimensions here do make sense. This is a 3 by 3. This is a 3 by 1. So I can multiply them because the inner numbers match here. This matches with this. And the result should be a 3 by 1. And the thing I've set it equal to is a 3 by 1. So it does make sense. Like this matrix equation is well defined. The product on the left can be done, and the resulting matrix is the same size as the matrix on the right-hand side that I've set this equal to. if we do the multiplication on the left, if I actually carry out the matrix multiplication over here, I get 1x minus 1y plus 3z in the first row. Then I get 1x plus 2y minus 2z in the second row. Remember, this is a 3 by 1. So it's just one entry in the first row, one entry in the second row. And the third row, I'll have the one entry, which is 3x minus 1y plus 5z. So we're saying this is the left-hand side, and that should be equal to the 4, 10, 14. And what's more, two matrices, the 3 by 1 on the left and the 3 by 1 on the right, are equal if and only if all their entries are equal. So this is the same as saying x minus y plus 3z equals 4. That's saying the first entry of this guy has to be equal to the first entry of this guy. Don't get thrown off by the fact that there's three things here. It's one entry. It's one number. They're all being added up. So this is one thing. One entry here, one number. It's just x minus y plus 3z. That's the number.
Did you mean to write 3 by 1 for that box or for that matrix?
Yes, yes, these are both 3 by 1s. This is 3 rows, 1 column, right? Here's your 3 rows, 1, 2, 3.
Okay.
1 column.
All right.
This is also a 3 by 1. 1, 2, 3, and then 1. So this is a single entry. This is a single entry. This is a single entry. All right. So when I multiply, when I set the first entry here equal to the first entry here, I get this equation. When I set the second entry here equal to the second entry here, I get x plus 2y minus 2z equals 10. And the third is 3x minus y plus 5z equals 14. And in order for this 3 by 1 matrix to be equal to this 3 by 1 matrix, I need not just one of these to be true, I need all three of them to be true at the same time. That's a system of equations. So this matrix equation at the very top is logically equivalent to this system of equations at the bottom. What that means is if you're given a system of equations, you can write it as a matrix equation. Thus, if I define A to be the 3 by 3 matrix, 1, -1, 3, 1, 2, -2, 3, -1, 5. I define the matrix X to be little x, little y, little z, and I define the matrix, I'll use maybe a big B, why not, to be 4, 10, 14. The system then the system of equations star can be written as the matrix equation A x equals B. And that looks a lot less intimidating. The solution to the system is the entries of the column matrix X, which is little x, little y, little z. So if you can solve this matrix equation for the column matrix X, like if there was some way to divide both sides by A and get X alone, then the entries of X you just read off are the solutions to your system of equations. This is the grown-up way to solve systems of equations. You rewrite them in matrix form, and then you divide both sides by the matrix A. You've seen how complicated multiplication of matrices is. So you might suspect that dividing matrices is also complicated, and you would be 100% right. First, we can't always do it. Just like you can't always multiply two matrices, right? They have to be the right dimension. But even under the appropriate dimension restrictions, you can't always divide matrices. Some matrices are like 0. You just can't divide by them. I'll tell you exactly what I mean by like 0. I'm going to give you a very, very particular definition of being 0-like. But there is a procedure. So what we say is we don't call it dividing by a matrix. We say you're going to find the inverse matrix. And then you're going to multiply on both sides by that inverse matrix. So let me introduce these notions. First, kind of questions about what's going on up here. How this system is equivalent to this matrix equation. Okay, then that's actually the end of 10.4. 10.4 is just how do I multiply, how do I add, subtract, multiply, divide matrices? And how can I think of a system as a matrix equation? 10.5 is all about matrix inverses. In order to talk about a matrix inverse, we need a handful of other concepts. And solving matrix equations like AX equals B. Just like normal, letters towards the start of the alphabet are going to be known quantities, and letters towards the end of the alphabet are going to be unknown quantities. So when I say AX equals B, it means I know the matrix A, I know the matrix B, I'm trying to find the matrix X. And we just saw that matrix equations like this are equivalent to systems of linear equations. Okay. I said what I want to do is divide both sides of that matrix equation by A, but there's no such thing as dividing matrices. What we can do is multiply by the inverse, kind of like reciprocal, right? Which kind of like multiply by the reciprocal is dividing for numbers. In order to talk about that, I need to talk about what it means to have an inverse matrix. And in order to talk about that, I need some concept of 1, right? So for numbers, we often say that like 3 has, I don't like this term, but inverse 1/3, right? And that's because 3 times 1/3 is equal to 1. This is something I'm sure everybody is familiar with. Well, what I need then to define an inverse for a matrix is 2 things. I need some idea of 1 over A. And I need some idea of the matrix 1. Right? So like 3 and 1/3 are both numbers. So A and its inverse should both be matrices. When I multiply those, I'm going to get another matrix. And that matrix should do the same thing that 1 does for numbers. What makes, so question, what makes the number 1 special? If you had to explain what the number 1 is to somebody without counting, mind you, no counting allowed. If you had to explain what the number 1 is to somebody, what would you say?
A prime number.
1's technically not prime. It's true that 1's only divisors are 1 in itself, but 2, 5, 3, 7, 11, 13, those are all primes, but that's not, but those numbers are not 1, right? I wouldn't say 2 does the same thing that 1 does, or that 5 does the same thing that 1 does. So a lack of other divisors is a thing for sure, and 1 does meet the kind of divisor criterion for primality. But let's look a little deeper. What else does 1 do with numbers?
Whenever it's multiplied to another number, that number doesn't change, it stays the same.
There you go. 1 is the multiplicative identity. Number 1 has the property that 1 times anything is that same thing. In other words, 1 times, I'll use x, is equal to x for any number x. This is the magical property that 1 possesses, which no other numbers possess. Think about it. If you multiply any number x by anything other than 1, you're going to get something besides what you started with. You multiply by 0, you always get 0. Multiply by 2, well, there's no number that when I multiply it by 2, I get that same number back. If you think about it, the only number which does that is 1. So the matrix 1 should have the property that matrix 1 times A is equal to A for any matrix A with dimensions that allow the multiplication. Now that last bit is kind of a gnarly sticking point. It's going to mean that we need more than one concept of matrix 1. In other words, I'm going to have a 2 by 2 matrix 1. I'm going to have a 3 by 3 matrix 1. I'm going to have a 4 by 4 matrix 1. I'm going to have one matrix versions of the number 1 for all the different size matrices that I might want to multiply it by. We call this the identity matrix. And it's really easy to remember. It's the square matrix whose main diagonal entries are 1 and whose off diagonal entries are all 0. So the 2 by 2 version of this, we call them I sub whatever the size is, they're always square, is 1, 0, 0, 1. The matrix I3, the 3 by 3 identity matrix, is 1, 0, 0, 0, 1, 0, 0, 0, 1. I4, the 4 by 4 identity matrix, would be 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1. And so on. It's the matrix whose diagonal entries are 1s and all other entries are 0s. I'm going to show you in the 2 by 2 case that if you take I2 and you multiply by any 2 by 2 matrix, you get that same 2 by 2 matrix. So if A is the matrix A, B, C, D, then I2 times A is 1, 0, 0, 1 times A, B, C, D. And what is this? Well, we're hoping it's A, B, C, D, but we should check. If I do the multiplication, I take the first row with the first column. So that's 1 times A plus 0 times C. To get the 2, 1 position, the 1, 2 position here, I take the first row and the second column. So that's 1 times B plus 0 times D. Let me put this in parentheses, so it's consistent notation. To get the 2, 1 position, I take the second row and the first column. So that's 0 times A plus 1 times C. And to get the 2, 2 position, I take the second row and second column. That's 0B plus 1D. And what is this? Well, 1 times A plus 0 times C is A. 1 times B plus 0 times D is B. 0 times A plus 1 times C is C. And 0B plus 1D is D. Hey, it works. And for the same reason, it works great for 3 by 3s, 4 by 4s, whatever. We should check that it works in the other direction as well. What is A times I2? Because remember, I times A is not necessarily the same as A times I. You change the order, shit gets fucky. Here, though, shit doesn't get fucky. So A times I2 would be A, B, C, D times 1, 0, 0, 1, which is A times 1 plus B times 0, A times 0 plus B times 1, C times 1 plus D times 0, and C times 0 plus D times 1. Little divider in here. And this, A times 1 plus B times 0, that's A. A times 0, B times 1, that's B. C times 1, D times 0, that's C. C times 0, D times 1, that's D. It works. So if A is any square matrix, and say n by n, then In times A is A. And A times In is A. These matrices do the same thing as 1. You multiply any other matrix by them, you get that other matrix back. In other words, they are the multiplicative identities, and that's the the word identity matrix comes from. Alrighty. Now it turns out that if you take a matrix that's not square, like a 2 by 3 or something like that, if you take an arbitrary 2 by 3 and multiply by I2 on the left, you'll get that matrix back. And if you take a 2 by 3 and multiply by I3 on the right, you'll get that matrix back. It even works if the matrices aren't square, but you have to use a different size identity matrix depending on the side you're looking at. For the purposes of solving systems and matrix equations, we'll always be messing with square matrices. Okay. So we have a concept of 1, which means we're ready to try and define the inverse of a matrix. Now that I know what 1 is, I can say what it means to have a reciprocal or inverse in matrix language. The study of these things, by the way, is called linear algebra, and it's a beautiful, huge field of mathematics. It's very important. We only talk about inverses for square matrices. So for an n by n matrix A, we say that the inverse matrix, the inverse of A, denoted A to the negative first power, just like 1/3 is 3 to the negative first power, denoted A inverse. It's also the same notation we use for function inverses, and this is why, right? Because matrices really are functions. This is the place where inverse and reciprocal actually do mean the same thing. The inverse denoted A with a negative 1 power like that is another n by n matrix satisfying 2 rules, and they're the same rules that inverse functions had to satisfy. If you do A inverse and A in this order, if you multiply them, then you should get the identity matrix of the appropriate size. Just like 3 times 1/3 or 1/3 times 3 should be 1. This is like 1/3 times 3 equals 1. And it needs to be true in the other direction as well. A times A inverse should also be IN. You need both of these to be true. This is the definition of the inverse of a matrix A. Why is this cool? So if you write a system of equations as the matrix equation AX equals B, and you know the inverse of the matrix A inverse, then we'll call this equation 1. We can multiply on the left, on both sides from the left, by A inverse to get, let's see, I start with AX equals B. And I'm going to multiply on both sides here from the left by A inverse. So I'll have A inverse AX equals A inverse B. Now the left-hand side, A inverse times A times X, that's n times x equals A inverse times B, because A times A inverse in either order is always In. And the matrix I, regardless of its size, always leaves you alone. So In times x is what? What do I get over here? How does this simplify? What does the identity matrix do when you multiply it by anything?
Does it stay the same?
Yeah, it stays the same. So In times x is just x. You get x equals A inverse times B. And remember, x is the column matrix that has our solutions in it. So that means you write your system as a matrix equation, then multiply on both sides by the inverse matrix, and you get your solutions. It's like a one-step thing to solve a system. Holy shit, that's awesome. Now this is mathematics. And there's no free lunch in math. So the work has to go somewhere. Instead of doing all those row operations to put your matrix into reduced row echelon form, you're going to have to do some kind of work to come up with the inverse matrix. There's no free lunch. You never get anything for free in math. So all that work has to go into finding something, just to go somewhere. The magic tool that lets us do this is the inverse matrix. So you may have guessed the work of finding the inverse matrix is every bit as intensive as row reducing the original to solve the system. There's good news and bad news here. Finding an inverse matrix is something computers do well. In fact, when you ask a computer to solve a linear system, that's what it does. You go into Wolfram or Symbolab or your favorite thing for cheating on our homework, and you ask it to solve a linear system for you. It's not row reducing. It's definitely not doing substitution or old-fashioned elimination. It's rewriting that as a matrix, finding the inverse matrix, and then multiplying on both sides by the inverse to recover your solution. That's what all those cheaty platforms do. And now you'll know how to do it too. So the big question becomes, all right, so remember this. This is the matrix with the solutions to our system. Once we find the matrix X, we win. Once we know this, we're done. We've solved the system. So how do you get X? You find A inverse, and you multiply B on the left by A inverse. That will always give you your solutions in one fell swoop. So the big question becomes, given a square matrix A, how do we find A inverse? There's more than one answer to this. I'm going to show you two ways. One of them only works for 2x2s. The other one works always. The one for 2x2s is very quick, very sneaky, and very useful in differential equations. The more general path is not so quick, not so sneaky, and is every bit as much a pain in the ass as solving the system any other way. But by learning how to do it, you will gain insight and hopefully push you towards understanding operator theory. All right. The inverse of a 2x2 matrix. if A is the matrix A, B, C, D, and A times D minus C times B is not 0, then the inverse of the matrix A is equal to 1 over AD minus CB times the new matrix you get by switching A and D, so flipping those guys over and negating C and B. So that's the matrix D, negative B, negative C, A. That's it. This is the inverse of a 2 by 2. And you see why we need AD minus CB to not be 0, because I'm multiplying by the reciprocal of that number here. This number, by the way, has a special name. This is called the determinant. Det A. It's the determinant of the matrix A. And it's what determines whether your matrix is invertible. If your determinant is equal to 0, then you sure as shit can't do this, because right here you would be dividing by 0. If your determinant is not 0, then you can do this. Nobody can stop you. So your matrix does have an inverse. The fastest way to figure out if a system of equations has a solution is to calculate the determinant of the associated matrix. It has a unique solution, I should say. If the determinant is 0, either you have no solution or infinitely many. But if the determinant is non-zero, then there is a unique solution. So let's do this really quick. Let's use this recipe to cook up the inverse of a 2 by 2 matrix. And let's go all the way and solve a system of equations with it. Well, no, let's just find an inverse. Let's do that. Find and verify the inverse of the matrix A equals one of the guys we played with earlier, 2, 1, 5, 3. Okay, so my determinant is 2 times 3 minus 5 times 1, which is not 0. So this is going to be 1 over A times D minus C times B. That's 2 times 3 minus 5 times 1 times the matrix that I get by flipping A and D and negating B and C. So that's going to be 3, 2. I flip those guys' position, and then I make these guys their opposites. So what's that number out front? This is 1 divided by 6 minus 5. That's 1 over 1. So that's 3, negative 1, negative 5, 2. And this is just 1 times that. 3, negative 1, negative 5, 2. And if you multiply a matrix by a number, remember that's just, you just multiply every entry of the matrix by that number. So here I multiply all these guys by 1. Of course, that doesn't do anything. 3, negative 1, negative 5, 2. So here's my inverse matrix. I claim this is the inverse. How could I verify that? What does it mean to verify? What's the definition of an inverse?
Multiply by the A matrix, see if you get 1.
Very good. I should be able to multiply A by A inverse and A inverse by A, right? Either order. And in both cases, I should get the matrix version of 1, the identity matrix. So this is finding Here, I'm going to verify. I made a stray mark on the page there. I'm sorry about that. So when I verify, I'll first do A inverse times A. Why not? That's 3, -1, -5, 2 times A, which was 2, 1, 5, 3. And this should be 3. So remember, rows with columns, 3 times 2 plus -1 times 5, so -1 times 5. That's row 1 with column 1. Now to get the 1, 2 position, I do row 1, column 2. That's 3 times 1 minus 1 times 3. Row 2, column 1, I take row 2, column 1. So -5 times 2 plus 2 times 5. And then row 2, column 2, -5 times 1 plus 2 times 3. 2 times 3. And what do I get? Well, 3 times 2 is 6. Minus 1 times 5, or plus -1 times 5 is 6 minus 5, which is 1. 3 times 1 minus 1 times 3 is 0. -5 times 2 is -10, plus 2 times 5 is +10, that's 0. -5 times 1 is -5, plus 2 times 3 is 6. -5 plus +6 is 1. So there you go, that's I2. Which is what we needed, right? And we need to check the other way. Remember, matrix multiplication is not commutative. It's possible that when you multiply in one direction, you do get the identity, and in the other direction, you don't get the identity. Those things absolutely exist, and they're called left inverses and right inverses. But it's different from being the big boy inverse, which is what we're interested in. Multiplying in the other direction, I've got 2153 times 3, -1, -5, 2, and we're hoping for the identity, but let's see. 2 times 3 plus 1 times -5. I felt like cat in here in just a second, I'm sorry. In the 1, 2 position, we've got 2 times -1 plus 1 times 2. Pouring outside, I'm gonna let her in, I'm sorry. Come on, kid. I know. Yes, I love you, very sweet. In the 2, 1 position, I take the second row, first column, that's 3 times 5 plus 3 times -5. Looking good so far. And then in the 2, 2 position, I take the second row in the second column. That's 5 times -1 plus 3 times 2. And you'll notice that the bits of arithmetic here are quite different, right? Like in the 1, 1 position here, I had 3, 2 plus -1 times 5. Here I've got 2 times 3 plus 1 times -5. It really is kind of neat that this works. The truth is, what's going on is we're taking linear combination of columns. So 2 times 3 is 6, plus 1 times -5 is -5. 6 plus -5 is 1. 2 times -1 is -2, plus 1 times 2 is +2 is 0. 3 times 5 is 15. 3 times -5 is -15. Add those, you get 0. 5 times -1 is -5, plus 3 times 2 is 6. You add those, you do get 1. So hallelujah. Again, we get I2. So we have found and verified the inverse of this 2x2 matrix. Wouldn't it be nice if there was a formula like that for all matrices? Yeah, it would. Yeah, it would. But there isn't. There just isn't. So if you have a bigger matrix, how do you find its inverse? I'll show you that. But maybe, yeah, let me show you how that is done, and then we can solve a system, okay? So Finding inverses for general matrices. This will work for a 2x2 also. It's just that the procedure I showed you a second ago is faster. So, you might as well use that. Here's what you do. To invert the n by n matrix A, one, augment A by IN. Remember what augmenting a matrix means. It means right next to that matrix, you write this other thing, like the augmented coefficient matrix. We had the coefficients of the system, and then the augmented matrix had that other shit over there that came from the right-hand side. First, you augment by the appropriate sized identity. Then you row reduce. You use row operations to make IN show up on the left. Of the augment bar. And through that process, A inverse will be the matrix on the right. The camera keeps drifting around. A inverse will be the matrix on the right of the augment bar. So what do I mean by augment A by IN? Let's write it down for a 3x3. I've got A11, A12, A13, A21, A22, A23, A31, A32, A33. There's the matrix A, and I'm going to augment it by the 3x3 identity matrix, which is 1, 0, 0, 0, 1, 0, 0, 0, 1. Then you do row operations until the thing on the left is the identity. So we do lots of row ops. Oh, Kitty's back. Hey, sweet girl. I love you. Yeah, stay down, girl. We do lots and lots of row ops until over here is 1, 0, 0, 0, 1, 0, 0, 0, 1. And as you do those row operations to turn this into this, this will turn into A inverse. That's it. That's how you do it. So those row operations that we were using to solve systems, it's the same thing, right? Like when you get your matrix into reduced row echelon form, where it's really, really easy to read off the solutions, you had to take your augmented coefficient matrix and turn the left-hand side into this. And we said, okay, as long as the stuff below here is 0, it's easy. But then you had to back substitute. If you really want to just read off the solution, get the matrix into this form, and then the stuff over here would be your solution. Well, if you want to find the inverse of a matrix, you do the exact same row operations. You turn the original matrix into the identity. And then as you do that, you do those same operations over here. So I'm thinking like when I do a row op, this is the first row. I do everything to that row. When I do a row op, this is the second row, and so on. As you do that, every time you fuck with something over here to get it closer and closer to this, you're going to be changing what's going on over here. And through that procedure, the thing that shows up over here at the end is the inverse of the matrix A. it's possible for this to fail. It's possible that in the course of running your row operations, you just get a row of all zeros here. You've seen that. And that means your matrix A is not invertible. I will show you a way to detect that ahead of time using a more general formula for determinants. That formula is unfortunately a little bit complicated. So let's practice this. Then we will talk about determinants. We're going to find the inverse of a 3 by 3. I could tell you to do 4 by 4s and 5 by 5s, but I won't. Okay, I just won't. It's too much work. If you can do 3 by 3s, you're good. So I'm going to start with the matrix 1, -2, -4, 2, -3, -6, -3, 6, 15. First, I augment by the identity. What does that look like? Well, that's 1, -2, -4, 1, 0, 0. 2, -3, -6, 0, 1, 0. -3, 6, 15, 0, 0, 1. I've taken the identity matrix of appropriate size, 3 by 3, same size as the matrix A, and just slapped it on there. I like the bar. Not everybody does it, but especially through this process, I encourage the bar. Now, row operations until the identity is on the left, which is the usual procedure. The same row operations we do to solve the system, same algorithm. Make this a 1, make everything beneath 0. Make this a 1, make everything beneath 0. Make this a 1. Then, now that this is a 1, make everything above 0. Now this is a 1, make everything above 0. Done. I'm going to try to do this reasonably quickly. My first row up, I'm going to kill this 2. So my new row 2 is my old row 2 minus 2 copies of my old row 1. Row 1 doesn't change. 1, -2, -4, 1, 0, 0. Row 2 is going to change. -2 times this plus this is 0. -2 times this is +4, plus this is 1. -2 times this is +8, plus this is +2. Got to do it over here. -2 times this plus this is -2. -2 times this plus this is 1. -2 times this plus this is 0. I'm going to go ahead and take care of the row 3, the 3, 1 entry here also. Row 3 is going to be my old row 3 plus 3 copies of my old row 1. So I'm going to multiply row 1 by 3 and add it to row 3. 3 times this plus this is 0. 3 times this is -6 plus this is also 0. 3 times this is -12 plus this is 3. 3 times this is 3 plus 0 is 3. 3 times this is 0 plus 0 is 0. 3 times this is 0 plus this is 1. You get good at row ops, this isn't too bad. The trick is being very careful with your arithmetic. All right, look what we've done. We've already knocked out all these. The fact that we got this one for free is really nice. Saves us an extra row operation. Just a coincidence, doesn't always happen. My next step, I look at this guy. I want to get towards reduced row echelon form. So I need the first non-zero entry in that row, right? First non-zero entry here is 1, first non-zero entry here is 1. I need the first non-zero entry in this row to be a 1. So I'm going to divide through here by 3. This has the unfortunate consequence of inducing a fraction in the 3/6 position. But my new row 3 is going to be 1/3 my old row 3. I'm not going to do anything else in this step. Don't use decimals. Fractions. It's fractions. Right. Well, we're getting somewhere. Now that I've got zeros everywhere down here and ones everywhere here, I want to make zeros up here, then a 0 here. So I need to kill the 2, I need to kill the 4. To kill the 2, I'm going to make my new row 2 equal to my old row 2 minus 2 copies of my old row 3. There will be some fraction arithmetic here, so we need to be brave. I'm going to copy down row 3 first. 0, 0, 1, 1, 0, 1/3. Row 3 is not changing. Row 2 is changing. So -2 times this plus this is still 0. -2 times this plus this is still 1. -2 times this plus this is now 0. That's why we're doing it. -2 times this is -2 plus this is -4. -2 times this is 0 plus this is 1. -2 times this is -2/3. -2/3 plus 0 is -2/3. And as you might have guessed, I'm going to go after the 4 in this run also. So I want to get rid of this -4 up here. So I'm going to multiply this by 4 and add it to that. My new row 1 is my old row 1 plus 4 copies of old row 3. 4 times 0 plus 1 is still 1. 4 times 0 plus -2 is still -2. 4 times 1 plus -4 is 0. 4 times 1 is 4 plus 1 is 5. 4 times 0 is 0 plus 0 is 0. 4 times 1/3 is 4/3. 4/3 plus 0 is 4/3. We are almost there, lads and ladies. The last thing we need to do is get rid of this -2. To do that, I'm going to multiply through row 2 by 2 and add it to row 1. So my new row 1 is my old row 1 plus 2 copies of my old row 2. And that's the last row up we have to do. So I'll go ahead and copy down the other rows. I have 0, 0, 1, 1, 0, 1/3, 0, 1, 0, -4, 1, -2/3. Now here comes the fun stuff. 2 times this plus this is 1. 2 times this plus this is 0. 2 times this plus this is 0. 2 times this is -8 plus 5 is -3. 2 times this is 2 plus 0 is 2. This is high. 2 times -2/3 is -4/3. Right? 2 times this is -4/3 plus this is 0. So that 4/3 in the top right goes away with our last row up because 2 times this is 4/3 and -4/3 plus this +4/3 is 0. Now you've got the identity on the left. This is I3. So this must be A inverse. Hence, A inverse is the matrix -3, 2, 0, -4, 1, -2/3, 1, 0, 1/3. And you could check that if you multiply this times the original matrix in either order, you will get I3, the 3 by 3 identity matrix. That's how you find inverse matrices. Now, rather than spending class time verifying that that matrix is the inverse, I'm going to show you how we use this to solve a system of equations. Questions on this procedure or any one of these steps? Okay. Let's solve a system. I'm going to tuck this in my pocket.
It's 250, Professor.
Okay, give me just one moment longer. I'm going to run a little over today. I apologize. If you got to go, you got to go. Just watch the video once it's up. Two more things to show you. I want to show you solving a system, and then I want to show you how to take 3 by 3 determinants, and then I'll let you go. You got to go, I understand. We're going to solve x minus 2y minus 4z equals 7. 2x minus 3y minus 6z equals 5. And negative 3x plus 6y plus 15z equals 0 by matrices. Specifically, matrix multiplication. So I'm going to write the system as a matrix equation. You'll recognize the matrix as the one we just inverted. That system is equivalent to 1, negative 2, negative 4, 2, negative 3, negative 6, negative 3, 6, 15, which is our matrix A from the previous example, times the column matrix X, Y, Z equals 7, 5, 0. The column matrix 7, 5, 0. All right, this is AX equals B. So what I need to do, right, is take AX equals B. Let me do this in black. And multiply on both sides from the left by A inverse. So A inverse times AX is equal to A inverse times B. We know that A inverse times AX is just X. So X is equal to A inverse B. And what was A inverse? Well, this matrix is the same matrix we just inverted. We know that A inverse is the matrix negative 3, 2, 0, negative 4, 1, negative 2/3, 1, 0, positive 1/3. That's the inverse matrix we just calculated. So X is equal to A inverse times B. That's negative 3, 2, 0, -4, 1, -2/3, 1, 0, 1/3 times the column 7, 5, 0. Let's go ahead and do this matrix product. Remember, this is a 3 by 3. This is a 3 by 1. Since the inner numbers match, I am allowed to multiply them, and the result will be a 3 by 1. Rows of columns, -3 times 7, plus 2 times 5, plus 0 times 0. That's your first entry. Your second entry, second row, and the column, -4 times 7, plus 1 times 5, plus -2/3 or -2/3 times 0. And then the last entry is 1 times 7, plus 0 times 5, plus 1/3 times 0. So what do we get? Well, -3 times 7 is -21, plus 2 times 5 is 10. And -21 plus 10 is -11. -4 times 7 plus 1 times 5 minus 2/3 times 0. That's -28 plus 5. -28 plus 5 is -23. And then the last column here, or the last row, sorry, last entry in this column vector is 1 times 7 plus 0 times 5 plus 1/3 times 0. That's 7. And remember x, that's the matrix, little x, little y, little z. So little x, little y, little z is equal to -11, -23, -7, i.e. x is -11, y is -23, and z is 7, or the solution is -11, -23, 7. That's it. So if you have the inverse of your matrix handy, or you have an easy way of computing the inverse of your matrix, then finding the solution is easy. It's as easy as just multiplying A inverse times B. That's it. That's the whole game. Not too bad, right? So that's how you solve systems like a grown-up. Write it as a matrix equation, invert the matrix, multiply on both sides from the left by the inverse of the matrix A. Oftentimes, again, in grown-up math classes, slightly more grown-up math classes, we'll just write the solution like this, as a column vector, rather than as a tuple, an ordered triple like this. If your matrix isn't invertible, of course, you can't use this. This only works if your matrix is invertible. And your matrix being invertible corresponds to a unique solution existing, right? If you can do this, then the system has to have just one solution, because it's a process that necessarily produces your solution vector with specific numbers in it. So how do you know if your matrix is invertible? That's where the determinant shows up. This is section 10.6. Determinants. I'm just going to show you how to do it. Okay, so recall, if A is a 2 by 2 matrix, A, B, C, D, then the determinant of A, det A, is the product of the diagonals subtracted. Main diagonal minus the off diagonal. AD minus CB. The determinant of a larger matrix is found by breaking it up into smaller matrices. If A is a 3 by 3, A, B, C, D, E, F, G, H, I, or larger, we find that A by what's called cofactor expansion, sometimes called Laplace expansion. The way this works is you get to pick a row or a column that you want to expand about. Then say I choose to expand about row 1. Just to show you. You assign pluses and minuses in a checkerboard pattern. To each of the entries of the original matrix. Then here, if I'm going about row 1, what I will do is I will say I'm going to run across this row, starting here. I write down the A and I write it down as positive because it has a little plus. And then I multiply that by the determinant of the little matrix I get by covering up row 1 and column 1. So if I cover up row 1 and column 1, then what's left is this little 2 by 2. This little matrix is called the minor. So here it's E, F, H, I. Then I write minus B, minus because it has a little minus here in my checkerboard pattern. And I multiply by the determinant of the little 2 by 2 I get by covering up the row and column that is in. So B is in row 1, column 2. So if I cover up row 1 and I cover up column 2, then I've got D, F, G, I. Now remember, I'm running about row 1. So my last step here is going to involve this C. I'm running across this row. I would write plus C because it has a little plus here according to my checkerboard pattern. And I multiply by the determinant I get covering up his row and column. That's row 1, column 3. So what's left is D, E, G, H. All right, and then each of the little determinants, you know how to calculate. They're 2 by 2s. So this would be A times EI minus HF minus B times DI minus GF plus C times DH minus GE. That's expanding about the first row. I could have expanded about any row or column I wanted, following that same pattern. So if I wanted to expand about column 3 here, I would start with C times the determinant of this guy, minus F times the determinant of A, B, G, H, plus I times the determinant of A, B, D, E. Let me do it again. That A this time will go about column 3. This is again called cofactor expansion. The numbers that we're multiplying out front are called cofactors. The little matrices are here are called minors. You don't need to know any of that to know how to do it. You just have to get a feel for what's going on. So I'm going to run down column 3. For each entry, I will take this thing and multiply it by the little determinant I get by covering up the row and column from that cofactor. So this is going to start with down column 3, starts with C. C has a plus, so this is going to be C times the determinant of the little matrix I get by covering up column 3 and row 1, which is D, E, G, H. Then I'll have minus F, I'm running down column 3, F has a minus, times the little determinant I get by covering up that column and that row, which is A, B, G, H. And then finally down in the third row, third entry in column 3, I have plus I times the determinant of the matrix I get by covering up this column and row, which is A, B, D, E. And I can write out what this is. This is C times DH minus GE minus F times AH minus GB plus I times AE minus DB. And if you're a very patient person, you can multiply all this out, and verify that they're actually the same thing. They better be, because I claim it's 2 different ways of calculating the same determinant. What this means is that for larger matrices, 3 by 3s, 4 by 4s, 5 by 5, 6 by 6, the way you calculate the determinant of a 4 by 4 is the same thing, cofactor expansion. You pick a row or a column to expand about, assign the checkerboard pattern, and then for each entry of that row or column, you cover up that row, you cover up that column, and find the determinant of the leftover matrix. So to find the determinant of a 4 by 4, you have to calculate 4 3 by 3 determinants. Just like to find the determinant of a 3 by 3 here, you had to calculate 1, 2, 3, 2 by 2 determinants. This is a way to take a determinant of an n by n and turn it into n determinants of n by 1 by n by 1 matrices. In other words, calculating determinants sucks. I have but one trick for you. Always expand. Always expand about the row or column with the most zeros. Because, if C and F are both 0, then I don't actually need to compute either of these. I just need to compute this. So that's nice. Almost done. Fact. Any square matrix A is invertible if and only if the determinant of A is not 0. And oftentimes, calculating determinants isn't that bad. For a 3 by 3, you can do it faster than you can find the inverse. So if you're like, the matrix has a bunch of fractions or decimals that don't really want to go through the process of finding the inverse, go ahead and calculate the determinant. If it comes out to 0, you can stop because it doesn't have an inverse. And when you do that, you should expand about the row or column with the most zeros. Now, there are some other cool things. Like, what do row operations do to determinants? They shouldn't be able to take a non-zero determinant matrix and turn it into a 0 determinant matrix. The row operation of the first kind, the one we do the most, where you add a multiple of one row to another, doesn't alter the determinant. If you swap two rows, that changes the determinant from positive to negative or negative to positive. It just changes the sign. And if you multiply through a row by a constant, it multiplies the determinant by that constant. There's two other things I would like you to write down here. I guess maybe just one other thing. I'll leave it at this. If a square matrix A has two identical rows or two identical columns, then det A is 0. The greater truth is that if it has any two linearly dependent rows or columns, then the determinant is 0. There's also something called Cramer's rule, which I would like to share with you. But maybe I shouldn't. I don't want to overwhelm. We're already way over time. So I suppose I will leave you free of Cramer's rule. You're not responsible for Cramer's rule. That's where we're going to stop it here, because I do want to spend Wednesday and Thursday talking about sequences and series, which are beautiful things, the notation for which you do need, because people get terrified of that shit in Calc 2 if they haven't seen it before. So that's what we're going to do. This is the end of our discussion on systems and matrices. Those of you who hung around, I really appreciate it. I know we've gone well over time here. So thank you for your patience and your attention. Please work hard on that homework. If you need help with anything, you can come see me in office hours. Yesterday, I know my office hour was really slammed. I didn't get to see a few people. I think at least one person waited quite patiently for a while while I was working with another student. I'm sorry. But I'll have another office hour today. I'm going to go over there right now. So that's it. I hope you guys have a pleasant rest of your day. If there's anything I can do to help you, don't hesitate to reach out, work hard on that homework, and I'll see you tomorrow.